Okay, so this is problems 31 to 40, and this number 31 is a more difficult question. And there's a couple ways to do this. I'm actually only going to show you one. I think the other one might confuse you. So the owner of a coffee shop, an amateur statistician, advertises the price of coffee on any given day will be randomly picked using a normal distribution. So they're telling us it's normal, with a mean of 135 and a standard deviation of 10. So 1.35 is our mean, and our standard deviation is 10 cents. If a customer buys a cup of coffee on 10 days, what's the probability he'll pay a total of $14? Well, here we're working with means. And so since we're doing this multiple times, we need to find out what the average is. So this would be 14 divided by 10 is $1.40. So the X bar in this case is $1.40, all right? Because I need to be able to compare it to the mean. We're not looking to compare $14, we're looking to compare the average. So because we have multiple days and we're looking at means, we need to be using Z equals X bar minus mu over sigma divided by the square root of n. So I want the probability that Z is greater than 1.4 minus 1.35 divided by 0.10 divided by the square root of 10. Because remember, the standard deviation of the X bars is the standard deviation divided by the sample size. In the calculator, I can do this as a norm CDF. Second vars, norm CDF, lower bound 1.4, upper bound infinity, average price is $1.35, then 0.1 divided by the square root of 10. And I end up getting 0.0569 equals 0.0569. So the question came up, how did I know that it was 14 over 10? And that's a really good question. All right, how did I know to divide this by 10? Well, for a couple things come to mind. First off, I know that the mean was 14, and my formulas are Z equals X bar minus mu sigma divided by square root of n. So in this case, it's like, okay, if I'm using this formula, I know I have to divide by 10. So that's actually how I knew. Alternatively, you're going, well, what if I wanted to use the $14? If you had chosen to use the $14, then I would have had to change this mean, because we'd had to sit there and go $1.35 plus $1.35 plus $1.35. I'd have to do it 10 times. And so then I would say, you know what? On average, his 10-day average would have been $13.50. Well, that's great, and I could do that. And then in which case I could use Z equals X minus mu over sigma, and that would be fine. I could do that. But I'd also have to adjust the standard deviation, just like I added $1.35 plus $1.35 plus $1.35 10 times. I'd have to do the standard deviation. But I can't just add standard deviations like that. I have to square them first, then come back and take the root of them. So ultimately, I'd have to do that 10 times. And if I had done that, 0.1 squared times 10, and then take the square root of that, I end up finding out this square root equals 0.3162. That's the square root of the 10 days. In which case, now I can go back and use this, and I can go 14 minus the 1350 over the 0.3162. And let's watch to see what happens if we've done that. Second vars, normal, CDF, 14, infinity, 1350, 0.3162. And we get exactly the same value. So there were two different ways to look at it, but it was probably more accessible if you converted it to an average so that you could use this formula, as opposed to going, I have to adjust the means, which I have to adjust the standard deviation. Motor vehicle death rates per 100,000 among the 50 states has a mean of 13.1 and the standard deviation of 4.9. So mean of 13.1, standard deviation of 4.9. While firearm death rates per 100,000 among the 50 states have a mean, and this is FA, mean of 12 and a standard deviation of 3.7. What would be the firearm death rate that has the same z-score as a motor vehicle rate of 15? So over here we have x equals 15. Now I could go through and calculate all the probabilities, but really all I need to work with here is a z-score. So z equals x minus mu over sigma, which in this case is 15 minus 13.1 over 4.9. (15 minus 13.1 divided by 4.9). So I end up getting, let me check my answer again. That looks right. 0.38774 equals 0.3877. So here we still have z equals x minus mu over sigma, and we're looking for x. Our mean in this case is 12. Our standard deviation is 3.7. And now we're using the same z-score to calculate x. So I just brought the z-score over here. So times the 3.7 plus 12. And I end up getting about 13.4. I end up getting about 13.4. Okay, which of the following is a true statement? The area under the standard normal curve between 0 and 2 is twice the area between 0 and 1. Okay, first off, that is false. And the reason it's false is because if we look at the normal curve, and this is 0, 1, 2, 3, because it's curved, the area between 0 and 1 is much greater than the area between 1 and 2. So consequently, those are not equal, all right? So that one's false. The area under the standard normal curve between 0 and 2 is half the area between -2, +2, and -2. This happens to be true, and the reason it's true is because it's symmetric about the mean. So 1, 2, -1, -2. So this area is the same as this area. Half is half over here and half over there. So that's going to be the same. So that's true. Populations P1 and P2 are normally distributed. Okay, so they're normally distributed. That means for both of them, the empirical rule applies and all probabilities are going to be the same for equivalent z-scores. They have identical means. However, the standard deviation of P1 is twice the standard deviation of P2. That means P1 is more spread out. That also means their z-scores can be set more spread out. So what can be said about the percentage of observations falling within 2 standard deviations for each population? All right, so what we can say is the percentages are identical. They both follow the empirical rule. The distance between, although the horizontal distance may be the same, different, I should say, the z-scores are the same, and so for similar z-scores, you're going to have exactly the same, for the same z-score, you'll have exactly the same probability, regardless of the shape, as long as we're working with a normal distribution. I should say, regardless whether it's really spread out or very tall and slim, the area is going to be the same, or the percentages will be the same for the same z-score. And remember, a z-score is just how many standard deviations something is from the mean. Okay, question 36. 36 is a plug and chug question. In other words, you get to run all the possibilities. So the waiting time for commuter bus is normally distributed. So we're working with a normal with a mean of 8 and a standard deviation of 2. So mean equals 8, standard deviation is 2. If there are 3,000 riders a day, which of the following is the shortest time interval associated with 2,000 riders? And it should say approximately 2,000 riders. It's not, I'm going to tell you, it's not exact in this case. So a couple things. Let's go back to the normal curve. So 0, 1, 2, 3, -1, -2, -3. There are more data points between -1 and 0 than there are between -2 and -1. There are more data points between -3 and -2 than there are between -2 and -1. You can look at it and go, this area right here is much smaller than this area, which is much smaller than this area right here. Now, -1 to 0 and 0 to 1 have exactly the same number of data points because they're the same area. They have the same area. Then we have -1 and -2 have the same number of data points. And then -3 and -2 and +2 and +3. So the tails have the least amount of data points, then here, and then the center has the most data points. So they want the shortest time. So the shortest time is going to be centered about the mean. So we're going to say the shortest time should be centered about here. But I need to go ahead and run all of these as norm CDFs. So second vars, normal, CDF, trials, or not trials, lower bound, 0, upper bound, 8.9 minutes. Mean is 8, standard deviation is 2. And I end up getting a probability of 0.6736, but they're not asking for probability. They want to be close to 2,000 times 3,000. And that's pretty close to 2,000. So this qualifies on a 2,000, but notice this has an 8.9 minute spread. Let's check this spread out. This spread out's only 1 minute. Let's see if it qualifies. Let's see if it is close on a 2,000. So second vars, normal CDF, lower bound 6.1, upper bound 7.1, times 3,000. Did not meet the 2,000, so we know this one's wrong because it's not close to 2,000. I go to the next one. Second vars, norm CDF. I change it from the upper bound to 8, and I multiply times the 3,000. It's like 986, not the right amount of riders. Then I go to the next one. And by the way, there's no, other than using your knowledge of the empirical rule, there is no other way to do this but plug and chug. That should be 999, it should be 9.9. Times 3,000. 1973, again, that's pretty close, but now look at our spread. Our spread is 3.8. That's closer, so that gets rid of A. This one has a much larger spread. It's at 7, so this is gone. So my best answer is D. It has the narrowest spread, it's the narrowest interval, and it has about 2,000 writers. It has about 2,000 writers. The SAT math scores for applicants to a particular engineering school are normally distributed with a mean of 68 to 680 and a standard deviation of 35. So mean is 680, standard deviation is 35. Suppose that only applicants with scores 700 above are considered for admission. What percent are considered below 750? So this is kind of interesting. All right, this is a given situation. All right, this is a situation where we're saying, given that they have a score above 700, what's the probability that it's below 750? All right, so let's calculate these. So first off, I'm going to start off with this. 680 and this is 700. So I want the probability that X is greater than 700, which is a probability that Z is greater than 700 minus the 680 over the 35. So when we calculate that out, second vars, normal CDF, we have a lower bound of 700, an upper bound of infinity, a mean of 680, and a standard deviation of 35. So in this case, about 28% of the applicants have a score above 700. But those are the only ones they consider. So now, let's do another calculation. And we need to find the intersection of 700 to 750. All right? We need to find the intersection of 700 to 750. So second vars, normal CDF, and I'm not going to show my work just because I'm going to run out of room. And I end up finding that this probability is 0.2611. So this is a situation where you have an intersection over given. This is going to be 0.2611 over 0.2838. 0.2611 divided by 0.2838. And we get about 92%. So about 92% of the qualified applicants have SAT scores below 750. All right, about 92% of those. And some people are going, well, how did you know it was given? It says what percentage of applicants considered, and it says only those with scores of 700 or above are considered. So since I knew that they had to have a 700 to be considered, that was a given situation. And remember, if you have a given, it's always the intersection over the given. Okay, problem 38. Which of the following statements is incorrect? In all normal distributions, the mean and the median are equal. That's true. Matter of fact, all symmetric distributions, that's true. But for the normal, the mean, the median, and the mode are equal. A normal distribution is determined by two numbers, its mean and its standard deviation. That's true, given that it follows the particular equation. What determines any particular one is its mean and standard deviation. All bell-shaped curves are normal. That is false. That is false. That's why when we were displaying and describing data, we said call it mound shape, don't call it normal, or call it bell shape, don't call it normal. We don't know if it's normal unless they tell us that or we tested it. Virtually all area under a normal curve is within 3 standard deviations, yes, 99.7%. And it doesn't matter how spread out it is. So it doesn't matter how spread it out it is, 99.7 is within plus or minus 3 standard deviations. Standardized z-scores have a normal distribution only if the original distribution is normal. This is true. Standardized z-scores only have a normal distribution only if the original distribution is normal. And you're like, well, what about the distribution of means? The fact of the matter is the distribution of means is normal. So the distribution of means is normal, therefore the standardized z-scores will be normal as well. Resuming recording, this is problem number 39. Taxi cabs in a metro area are driven an average of 75,000 miles per year with a standard deviation of 12,000 miles. So we have a mean of 75,000, standard deviation of 12,000. What is the probability a randomly selected cab has been driven less than 100,000 if it is known that it has been driven over 80? So basically, once again, we have a given situation. Given that it was driven over 80, what is the likelihood that it was less than 100,000? So let's draw our graph for the given part because the given is always in the denominator. This is the 80, and we're up this way. So the probability that z is greater than 80 minus 75. Point 3384, so about 30.3384, about 34%. And then we have the second part. And by the way, this is actually me actually being cruel to you guys. This way I let y'all, by giving a problem like this, you get to do the normal distribution twice. So it's, even though it's only one problem, you get twice as much out, twice as many attempts at practicing the normal. So we want the probability that it's between 80 and 100,000. So this is 80 is my lower, 100 is my upper. And once again, I should be showing my work, but we won't have one on like that on a test. So normal CDF, 80 is my lower, 100 is my upper. Mean is 75, standard deviation 12. And we have 0.3198. And please remember, once again, it's always intersection over given. So 0.3198 divided by the 0.3384. Once again, if you ever get a probability greater than 1, you messed up. So approximately 0.94, which is what we